Back to the Physics Bootcamp addendum. We come to problem number 10 now. It says a particle of mass 2 times 10 to the minus 15 kilograms and traveling at 0.95 the speed of light c comes crashing into a particle of mass 5 times 10 to the minus 14 kilograms originally at rest. Assume the collision is perfectly inelastic. A, calculate the final beta of the system, and B, calculate the percent loss of kinetic energy. This is similar to a typical inelastic momentum collision problem that we would see in mechanics. However, the equations of motion we have to use are the equations of relativistic dynamics. Since the speeds are at relativistic speeds, we can't just simply use momentum equals mv. Kinetic energy is half mv squared. Okay, so I'm going to write down now the equations of relativistic dynamics, and then we use those equations for this situation. Okay, mass m going at a certain velocity v, in this case it's 0.95 the speed of light. This mass m that the particle has, we're going to call the rest mass m0, and that's equal to 2 times 10 to the minus 15 kilogram. This other object has m0 and then it's 2, mo1. Okay, so this object is originally at rest and its mass is 5 times 10 to the minus 14 kilogram. Okay, the equation for the momentum that this object has, the equation for relativistic momentum, is gamma m0 v. Notice it's very similar looking to the regular equation where momentum is mv, except we're going to use the rest mass. This is known as rest mass, and then gamma is the relativistic factor. For objects that are going at slow speeds, gamma is approximately 1. So for non-relativistic speeds, the equation becomes mv. But for relativistic speeds, the factor gamma becomes bigger and bigger and bigger and bigger. Remember what the gamma definition was. Gamma is defined as 1 over square root of 1 minus beta squared, and then beta is defined as v over c. When v is 0, gamma is 1. So we could draw a graph of gamma as a function of v. When v is 0, gamma starts out at 1. And for regular non-relativistic speeds, it pretty much stays close to 1. And then this is the speed of light c. So the gamma goes up, starts getting bigger, 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 bigger. When you start getting half the speed of light, then the gamma starts getting bigger and bigger and bigger. Okay, at half the speed of light. Then it starts getting really big when you get to 90% the speed of light. When you put here 0.9 and you square it, now you're going to start getting bigger and bigger numbers, and it asymptotically reaches infinity. As the speed of light approaches c, 1 minus 1 squared, beta becomes 1, right? 1 minus 1 squared, that approaches infinity. So the factor gamma really becomes significant when you're going about 90% or greater than the speed of light. Okay? So that's the equation for linear momentum. The equation for energy, the total energy, is equal to gamma m0 c squared. Now you've seen the equation E equals mc squared, and oftentimes when we say E equals mc squared, we're just more interested in the rest energy, m0 c squared. That's known as rest energy. It's just this portion of the equation, okay? But the total energy is m0 c squared times the relativistic factor gamma. This is equal to the rest energy, E0, plus the kinetic energy. So even when an object is at rest, since it has mass, and mass and energy are equivalent, it also has rest energy, plus if the object is moving, it has kinetic energy, right? So what would the rest energy equal? m0 c squared, right? Plus the kinetic energy. So what would be the relativistic equation of kinetic energy? So since m0 c squared plus kinetic energy is equal to gamma m0 c squared, if I want to solve for kinetic energy, the m0 c squared comes to this side and you get gamma m0 c squared minus m0 c squared, and then you get gamma minus 1 m0 c squared. So this is the equation for kinetic energy. Gamma minus 1 m0 c squared. The equation for total energy is gamma m0c squared, linear momentum is gamma m0v. We could also have another equation that connects the energy and the momentum. That equation is going to be, if you square this and you square that, and you can spend some time to prove this equation, then what you're going to end up is E squared is equal to E0 squared plus momentum times the speed of light, quantity squared. All you have to do to prove it is you have to square it on this side, and then on the right side you have to square this equation, m0c squared, and then you have to multiply this by c and n squared and show that the left side is equal to the right side. So this is just simply putting together the previous equation, and then you get another equation. So this, in summary, are the equations of relativistic dynamics. Okay, so now let's apply that to this case. We know that when this has a certain momentum, it's going to come and collide with the second mass, and you're going to have m01, m02, and together they're going to move forward with a certain velocity, right? What has to be conserved in this case? Well, the quantity that is conserved is only the linear momentum, not the kinetic energy, because this is a typical inelastic collision problem, right? So the linear momentum initial, P total initial, must equal to P total final. Okay, so what's the P total initial? Well, we have M01. Okay, so we're going to have gamma M0. So we're going to have gamma M01 times V initial. Okay, and that's going to equal what? The total. So the total momentum after the collision, well, we're going to have a similar equation, gamma final, and this is gamma initial, right? Gamma final, which I don't know. And then what's the total mass? So I'm going to go, I need to know the total rest mass of the system, m01 plus m02 times the final velocity after the collision, right? So now let's do this. Let's calculate what is the gamma if the velocity is 0.95 c. So gamma initial is 1 over square root of 1 minus 0.95 squared. All I need to know is the ratio of its speed to the speed of light, and then I'm going to square that. So I'm going to do 1 minus 0.95 squared. I'll get a certain number, then I'll square root it, and then I will invert it, reciprocate it, and I get gamma initial is 3.203, and it's a unitless number. So that's the initial gamma, so which I could put over here, 3.203. What's the initial mass? 2 times 10 to the minus 15. The initial velocity is what? 0.95 the speed of light. Okay. What's the final gamma? I don't know. Okay. What's the final mass? I have to add these two. 2 times 10 to the minus 15. And what is this? Well, this is actually this is actually heavier. So we could write this so that it's the same power of 10 as this one. It'll be better that way. If it's 5 times 10 to the minus 14, what is it? Well, I can add a 0 here, and then it'll be 10 to the minus 15. So I can basically take the decimal point 1 over, and then I would have to go back one more space. So it'll be 50 times 10 to the minus 15, and then this is also 2 times 10 to the minus 15. So what's the total mass now? 50 plus 2 is 52. 52 times 10 to the minus 15. 52 times 10 to the minus 15, V final. And what will happen? And then here I had 2 times 10 to the minus 15, right? The 10 to the minus 15, 10 to the minus 15 will cancel. And then I can write what I have here, 203. And then I have 2. I have 0.95 C. And then the 52 comes down to the bottom. And then that will be equal to V final which is here. And then gamma final is 1 over square root of 1 minus V final squared over C squared. Okay? So what I'm going to do here is I'm not even going to put what the speed of light is, because I only want to know what the final velocity is in terms of the speed of light. So I'll just keep it as c. So basically I'm going to calculate this now and then square both sides. So here's what we have. I get 0.01369,665, and then I'll get c squared, and I'll square this side, v final squared over 1 minus v final squared over c squared. 0.01369,665, 1 minus v squared over c squared, and then there's a c squared here, and then that's equal to v final squared. Okay? Then I'll distribute this in, and I'll have 0.01369,665 c squared minus 0.01369,665, and then the c squared will cancel the c squared. V final squared is equal to v final squared. Then basically what's left to do is I take this to the other side, and I'll take 1 plus this number. So basically I'll end up just getting, I'll put the equal sign here, so I'll add 1 plus this number, 1.01369,665, v final squared. Then I'll take this and divide it into here, 1.01369,665, and then this will disappear, and then I'll square root both sides. So square root this, square root this, square root this number. So basically, since I had c squared, when I square root c squared, I'll get c. So now what's left to do is take this number, 0.01369,665, divided by 1 plus that number, 0.116, the speed of light. Okay, so what is my beta? My beta is just 0.116, because it's the ratio of my velocity to the speed of light. So my beta final is 0.116. Okay? Now how do I find the percent loss of kinetic energy? Just similar to what we used to do in regular mechanics, we would solve for what is the initial kinetic energy, and then what the final kinetic energy, and then take the percent difference of those. Right? What is the initial kinetic energy? The initial kinetic energy is equal to gamma minus 1, gamma initial minus 1, m0 c squared. Right? So initial kinetic energy, gamma initial was 3.203 minus 1. The initial mass was 2 times 10 to the minus 15. And then the speed of light squared, well, that's 3 times 10 to the 8 squared. Okay, and what am I going to get here? Well, I'm going to get 2.203, because you're subtracting 1. 2.203 times 2 times 3 squared is 9. So you get 39.654, and then what's the powers of the 10? This is 10 to the 16th times 10 to the minus 15. So that's what? 10 to the 1, basically. So basically this comes out to be 396.54 joules was the initial kinetic energy of the incoming particle. Okay, what is the final kinetic energy? Well, we're going to do similar. Let's calculate the final gamma. Gamma final is equal to 1 over square root of 1 minus beta final squared, 1 minus 0.116 squared. So 1 minus 0.116, I'm taking the final velocity of the combined particle, Then I'm doing the same things to get the final gamma. That's gamma final. So then the final kinetic energy will be gamma minus 1, gamma final minus 1, m total 0 c squared. So kinetic energy final, I subtract 1 from this. And then the total mass was what? Remember, it was 52 times 10 to the minus 15. 52 times 10 to the minus 15. And then the speed of light squared, I can put it quickly. That'll be 9 times 10 to the 16th, right? Because you have to square the 3. So 9 times 10 to the 16th. So basically I'm subtracting 1 from the gamma that I just got. Subtract 1. Then multiply it by 52. And then multiply it by 9. Okay, so you get kinetic energy final 3.1808 times 10 to the 16th, 10 to the minus 15 is 10 to the 1, which is 31.808 joules. So the initial kinetic energy 396, the final kinetic energy 31.808 joules. So a lot of the kinetic energy has been lost. So the percent loss, 396.54 minus the final kinetic energy, 31.808, absolute value over the initial kinetic energy. Okay, 396.54 minus 31.808 divided by 396.54 times 100. So it's equal to 91.98% loss of kinetic energy. Okay, so now you can see a lot of the kinetic energy is lost because this is an inelastic collision. So a quick, fast particle colliding with a heavier particle, because remember the one that was at rest was heavier, so most of its kinetic energy is lost. So now you can see how to do similar calculations to what we used to do in regular mechanics, but apply the equations of relativistic dynamics. Okay. Next, I'm going to solve an elastic collision problem, again using the equations of relativistic dynamics. Okay. Thank you.